All right, so far in our COVID model, we were dealing with three kinds of people. One is the number of sus people, so those who might have COVID. People I, which is the number of infected people, those who actually have COVID. And R is the number of people who recovered from COVID. And as we said before, we won't really care about R because we can solve for R in terms of S and I. So we'll just ignore that. And we had our reduced equations, so our system of ODEs. So we have a reduced model, namely S prime of t is minus SB over N, SI, and I prime of t, which was B over N, SI minus gamma I. And let me just reiterate what all those constants mean. So Queen B is the number of people a sick person infects a day. The number of people a sick person infects per day. Gamma was the recovery rate. Wait. Let's say if gamma is 0.25, then 25% of people recover per day. And finally, N was the total population, which we saw is actually constant. Okay. And now what we would like to do, we would like to simplify this a little bit further by defining a new unit of time. So this is called rescaling time. Because if you think about it, an Earth Day is quite arbitrary. So let's define a new kind of day. So let that tau, in other words, define a new unit of time, time tau, which you can think of it as a Peyam day as follows. So suppose on average, someone recovers in 4 days, then a Peyam day would be 4 days. So we will assume everyone will recover on average in 1 Peyam day. So in other words, tau equals 1. 1 Peyam day just means the length of time it takes for someone to recover. Now remember, the length of time it takes for someone to recover was 1 over gamma. So we assume 1 Peyam day means 1 over gamma Earth days. So if gamma is 0.25, then 1 Peyam day is 4 days. And that was, remember, the mean residence time. Time of disease. Which we can write in a nicer form. So this is the same thing as gamma t equals 1. And so just by comparing those two equations, it makes sense to suggest that tau is gamma t. So in other words, define tau is gamma t. And then the next thing we want to do, we want to redefine S and I in terms of this new time tau, but more precisely, not S and I, but the proportions. And that's what we call X and Y. Let X and Y be the proportion of susceptible people and the proportion of infected people, because remember, N is the total population in terms of tau. That is, X of tau is, again, the proportion of susceptible people, so S of T over N, because remember, N is the total population, and if tau is gamma T, then T is tau over gamma, so this is really S of tau over gamma over N, and same thing with the proportion of infected people, I of T over N, and that's I of tau over gamma over N. And again, what X and Y are is just a fraction of susceptible and infected people, of sus and infected people. And then what we can do, we can then rewrite our SIR model, SIR, in terms of X and Y using the chain rule. So this you can see in the notes because it's a bit more involved. And it turns out you then get the following, which we like to call the rescaled model. So the model in this new unit of time, which is simply X prime of tau is minus R not X times Y, and Y prime of tau is ROXY minus Y, where R naught is B over gamma. And I'll explain what this means, but this is really the differential equation that we will study, so we'll find the equilibrium points and stability. But I do want to mention the reason we're doing this is because there's a particularly nice interpretation of R naught in terms of our model, because R naught, what this really is, that's B times 1 over gamma. Now remember, B is the number of people a sick person infects per day. Per day. And 1 over gamma is the time, is how long a person is sick. A person is sick. So R naught is just kind of the damage a sick person does. So it just says how many people a sick person infects while they have a disease. People a sick person infects in total. And in fact, before doing this rescaling in time, we wouldn't have such a nice interpretation. But now we have it, and in the next video, we will actually study this differential equations model. And you will see there will be very, very cool interpretation.